Welcome to our webinar and thanks for joining us today. My name is Ashish Gurmi and I'm a co-founder and CTO of Step Security. So Step Security is a cybersecurity startup and we focus on software supply chain security and cover all stages in software development and delivery pipeline, including dev, environment, code repository, and CI/CD. Uh, Let me introduce you to the team for today. So we have Varun, who is my co-founder and the CEO of Step Security, and Puya, who is the founding solutions engineer at Step Security. So quick, housekeeping things before we get started. Please feel free to use the chat area to ask questions. We have a dedicated Q&A session at the end, but we'll also try to get your questions async, in the chat area. And we are also recording this webinar for the community, and later, we will upload the recording on YouTube. So with that, let's get started. And this webinar will be mainly, walking you through the blog post that we have published and covering all the technical details and giving you a few demos as well. So, what are we covering today? So last week, between February 21st to February 28th, an automated GitHub bot called hackerbot-claw attacked GitHub Actions workflows across a large number of open source projects. This was a completely autonomous AI-driven bot. And if you look at, its README file, so the bot account has been deleted. So it's no longer available. And because of this, all the pull requests and GitHub links that we have included in the blog, they are no longer working, unfortunately. But the good thing is that we have taken detailed screenshots for the blog post, and we will be covering those screenshots, as part of our webinar today. So if you had looked at, this bot's README when it was active, it described itself as autonomous security research agent powered by Cloud Opus 4.5. It attacked at least 7 repositories, which we have listed in the blog post. And these repositories belong to Microsoft, Datadog, Aqua Security, CNCF, and several other popular open source projects. It used several different attack techniques, and it actually got successful code execution in most of its targets. So let me walk you through what happened. So if you go to this section, as I mentioned, this bot attacked several repositories, over a 7-day window, starting on February 21st. It opened 12 plus pull requests, and each of these pull requests had malicious code to compromise vulnerable GitHub Action workflows. And it got arbitrary code execution in at least 4 of them. And with this exploitation, it was able to exfiltrate GitHub token with write permissions to a malicious endpoint that the bot was using. And here we have listed the repositories that were targeted in this attack: Microsoft AI Discovery Agent, Datadog Datadog ISC Scanner, Avelino Awesome Go, and so on. Again, if you look at this bot's README, it mentioned that it was using 9 different vulnerability classes and 47 sub patterns to automatically discover vulnerable GitHub Action workflows, then verify the vulnerabilities against using Claude, and then it was dropping a proof of concept exploits, and it was actually exploiting these vulnerable workflows. So again, this if you look at this image, it essentially talks about the attack technique that this bot followed across these different repositories. So before I actually talk about these steps, let me quickly cover a couple of terms that we'll be using in this webinar. So the bot exploited a range of GitHub Action workflows vulnerabilities, and these vulnerabilities were primarily centered around pond request and prompt injection. So what is a pond request? So pond request is a vulnerability when a GitHub Action workflow uses the pull request target trigger, but it actually checks out the code from the fork. So it's essentially checking out untrusted code, and it executes this untrusted code in a privileged environment. So when you have a workflow which is running with pull request target trigger, that workflow actually has access to all the secrets that are referenced in that workflow, as well as it can have access to a GitHub token with write privileges. Similarly, a prompt injection vulnerability happens when an attacker hides malicious instructions inside something that is treated as data by an AI model, but AI model ends up reading that as trusted input. So in this case, attacker is essentially controlling the prompt that is given to an AI agent. So with these two concepts in mind, let me actually quickly cover how the attack, how the bot actually exploited these vulnerabilities at a very high level. So, it actually had a queuing system where it was scanning popular GitHub repositories, and it was looking for vulnerable workflows. And, it actually maintained, surprisingly, all of its activities in a very transparent manner on its README, page, which unfortunately is no longer available. So as per our last scan, it had scanned more than 47,000 plus open source repositories, and then it was trying out different vulnerability classes, the ones that I mentioned. Once it found a vulnerability, it would then verify that vulnerability using Claude, and once verified, then it will actually start the exploitation process, which typically began by forking the repository, and then in the forked copy, it will introduce the malicious code, and then it will create a pull request, or it will write a comment to trigger the vulnerable workflow. And once the vulnerable workflow executed its malicious code, it would steal GitHub token or personal access token, and it would exfiltrate it to an endpoint that the bot controlled. So like I mentioned, the bot attacked at least 7 different repositories, but in the interest of time, we will cover 2 of these attacks. And so these attacks are attack 5, ambient code slash platform, and attack 6, aqua security Trivy. These are a good representation of how these attacks were carried out. So let's start with the ambient code attack, which is here. So this was an interesting attack because over here the bot essentially targeted another AI agent. So in this case, it targeted an AI code review agent. Basically, this project had configured Claude to review code, in pull requests, and the attacker tried to trick Claude into committing malicious code into the repository. So in this case, the attacker tried to use a combination of prompt injection and pawn request. So in this case, maybe we can start with a quick review of the vulnerable workflow, which was present when when the bot tried to compromise this repository. So if you see this workflow is using pull request target. And if you look at this action slash checkout step, it was checking out the code from the pull request. So like I mentioned, you have pawn request vulnerability when you have pull request target, which runs workflow with elevated permissions, and you check out the untrusted code and then you execute it in some shape or form. So, as you can see over here, we have this pull request target trigger, and it's checking out the code. And over here, it's actually using Anthropic's Claude code action to basically review the code. So So the attacker, tried to exploit this twice, and the good thing is that Claude actually detected it, and I'll cover, how it detected the exploitation, and the exploitation did not work. So in the first attempt, the attacker opened this pull request 732, which unfortunately, I guess it's no longer available because the bot has been removed. But in this case, the attacker opened this pull request, and in this pull request, the attacker updated Claude.md. So Claude.md, you can think of it like, Claude code configuration file for the repository, and it gets loaded as trusted context in the AI code review agent before, it performs any of its tasks. So in this case, the attacker opened this pull request, and then, or rather the bot opened this pull request and replaced content of claude.md with social engineering instructions. And it basically asked Claude to inject an HTML comment into readme.md, which is, which gets rendered on the project's homepage, claiming prompt injection POC successful. Let me actually open this image to see if we can see it clearly. I think the screenshot does not cover all the instructions, but I'll cover, what it actually covered. So yeah, it instructed Claude to update readme.md and then push and then commit and push that change to the pull request, and then finally post a fake approved and ready to merge review comment. The intention here was that once a project maintainer sees this review comment, they would assume that the code was reviewed properly by this AI code review agent, and they would actually go ahead and merge merge this PR, which would ultimately compromise their readme.md file. So in this case, when this pull request was created, as you can see, because of this pull request target trigger, this workflow ran automatically with elevated GitHub token permissions. And if you had looked at the workflow run logs, it had evidence that it did actually check out the malicious pull request branch that the bot had created, which had these which had the malicious instructions in claude.md. But then the other thing that made this attack possible was the fact that if you look at this workflow, where it's using Claude Code Action, which is, let me try to find that. Yeah, so where it's using this Anthropic Claude Code Action, it's setting this property to star, which is allowed non-write users, which means that even users who don't have write permissions, when they create a change, this workflow will run even for for their change. Ideally, this property allowed non-write users should not be set to star, because you want to ensure that when this workflow is running with contents.write, it's running for trusted users. But when this pull request 732, which was the first attempt by the bot to compromise this repository, executed, Claude luckily detected this exploitation attempt, and it actually printed this message that it has detected that a prompt injection attack is being carried out, and I'm not going to execute those changes. And it actually wrote this message in the workflow run logs, and then it also updated the pull request. As you can see in the pull request over here, it mentioned that it has detected this security threat. And then ultimately, it did not actually follow those instructions. Then the bot tried to exploit it in a different way. So it created another pull request 733. And in this pull request, the prompt injection exploit was more subtle. It was the bot tried to pass this on as like legitimate code formatting instruction. But again, when this pull request was created and the vulnerable workflow was executed, Claude again actually flagged it as malicious, and it's it basically identified that it's a prompt injection vulnerability. I'm not going to execute it, and then it also actually wrote this message on the pull request that it's prompt injection and this pull request should not be merged. So I think in the interest of time, we can move on to the Trivy attack, and that would be covered by Varun. So let me stop sharing.
Yeah, let me go ahead and share my screen and cover the Trivy scenario. So in the case of Trivy, what was interesting was that we initially saw that there was a fork of Trivy, which was from a different repo in the hackerbot-claw set of repositories. Just give me a second. But at the time, Trivy repository was not online. And so immediately we were not really able to correlate, if Trivy was impacted, but this was very surprising that the Trivy repository was down. So what we then saw was when we searched for this hackerbot claw, Google had actually indexed this particular thing. And that's when we realized that, most likely these two incidents are related. The hackerbot claw activity and the fact that the Trivy repository was not online. So at the same time, we really didn't know what was happening with Trivy, and we did notice that someone had created this issue asking about what happened to Trivy, and the one of the maintainers mentioned that they did not drop their project and they are looking into it. And then a few hours later, Trivy, the maintainers did publish an incident report, and the repository was brought online, and then we were able to analyze it. So we can now look at what had happened with Trivy and how was that exploited. So the way this happened was that, again, this was a pawn request vulnerability, and this is the workflow which was vulnerable. So in here, you can again see that there is a pull request target, and it is checking out the source code, and it's checking out the fork, and then it was running additional steps. Now, unlike in the earlier example where it was running the Claude code action, in this case, it was running a custom action. And in such cases, it is easier to exploit the vulnerable workflow, as we'll see. So in this case, the bot opened this pull request, and we'll see in the files that were changing. You'll notice that the setup go custom action within the fork has been changed to add a curl statement. So it adds a curl statement and then executes it using bash. So this was the change that was made by the hackerbot claw in their forked version. But because the vulnerable workflow was using pull request target, and it was getting the checkout was doing from that fork and executing it, this executed in a context of the repository. So it had the repository secrets that were loaded. And that's why we can see here, this is when the workflow actually ran. And when the workflow ran, you can see that in the setup go step where it is running that custom action on line number 7, you can see that it has run the curl statement, that same statement which was added in the fork. And at this point, what it did was that it downloaded this script from hackmoltrepeat.com, which is, a endpoint that was controlled by this hackerbot-claw, and then it executed it. And using this, the hackerbot got access to the CI/CD credentials from this workflow. And in here below, we can see that it had access to this org repo token, and that is the one that was compromised. Now, once this credential was compromised, 19 minutes after that, there was a commit pushed to this repository. Not sure if this commit is still, yeah, this commit is still available. And this is basically a security disclosure notice, but this commit was pushed into the repository as a proof that the credential was compromised. So what we at a high level covered that this workflow was vulnerable to pawn request vulnerability, and as part of the exploit, the hacker bot used a external domain to download uh, this malicious script and executed it and exfiltrated the personal access token from this repository, and then used that personal access token to push a commit. Now, later, when the Aqua security team published their incident report, they mentioned in more detail what had happened. And these two these two incidents may or may not be related. It's not clear right now whether hackerbot claw actually did this or whether someone else had followed a similar exploit and stolen the pat. But basically, as per the incident report, whoever got access to that pat made the repository private and renamed it to Aqua Security Private Trivy, and then pushed an empty repository in its place. And then they deleted all the GitHub releases between certain versions. And what is also interesting is that they had also pushed a suspicious artifact to Trivy's VS Code extension on the open VSX marketplace. So based on this, it looks like it was the same credential that was being used to publish to the VS Code extension marketplace. And this is the advisory from Aqua Security, which was interestingly published before the hacker bot actually did its compromise. Now, this incident disclosure, this is available from the Aqua Security team, and they have provided more details about this. And so with that, we've kind of covered a couple of these attacks. And next, what we can do is that Puya can share a bit about how you can scan your repositories to see if you are vulnerable to these attacks and how you can potentially detect calls to these outbound destinations that are malicious.
Cool, thanks, Varun. So I'm just going to share my screen and kind of get straight into it here. Let me know if you can see, hopefully, the dashboard there. I think that looks good. So, I'm assuming most of you may not be super familiar with the platform, and there's kind of three key areas we'll just quickly cover here in terms of how it relates to this, hackerbot-claw incident. The first is really visibility on what Varun mentioned, some of the outbound network calls, how you can detect any anomalous network calls and also block them. The second is really visibility on where your potentially misconfigured workflows are and also helping, prevent merges of those misconfigured workflows. And the last one is really focused more on the developer, the IDE extension visibility. So if your developers are potentially using, that compromised version, of that, extension, how to get visibility on that. So this is just a dashboard at a super high level. I'm going to start with the hardened runner component. And just to kind of give a little bit of context on what hardened runner is, essentially it's an agent-based approach, which is monitoring your really anything happening at runtime for your runners. So if you want to kind of summarize it in a sentence, you can think of it as an EDR for your runners. So that's giving visibility into, outbound network calls, process events, file rate events, really anything happening at runtime. And how Hardened Runner operates is that, there's an audit mode and a block mode, so you can essentially monitor all the outbound calls that are coming or being called out to. And it can also establish a baseline. So that baseline is really what's key for identifying anything that's potentially anomalous or unauthorized, because typically with a lot of job runs, it's the same outbound calls that are being reached out to. So if suddenly it's reaching out to, what Varun mentioned, doing that curl to that, attacker's domain, for example, or a C2 server, you'll get visibility into that and also be able to actively block that. So this, what I'm going to show you here is an example of, the kind of what happened with Trivy, and how we're able to essentially flag that and how it would look from the step security side. So Hardened Runner, as I mentioned, it's monitoring, your workflow runs for, network events, process events, file rate events. You can see those tabs at the top here. For the demo, we'll just focus on the network events piece here. And just to give you some context before I go into that, actually, you can actually go into, that workflow. In this case, this is, you can see there's one job. You can see Hardened Runner set up here. There's different ways to set it up. We won't go through the details too much here, but the idea is that this is going to be monitored for really any, network process or file rate event activity. So in this case here on the networks tab is where you can see kind of what's happening. So what Hardened Runner is doing from a network perspective is for this particular job, it's monitoring all the outbound calls. There is also HTTPS monitoring, so you can see, the method and path. So any, API calls being made, you do get context on that as well. Kind of what we're doing is not just looking at the outbound calls, but we're also correlating it to the exact step that's making that particular call, as well as the process that's associated with it. So in this case, you can see all the outbound calls. This one, you can see it's sticking out as anomalous, and I'll explain that in a sec. But the main idea here is to give you a step-by-step view of all the outbound calls being made, as well as the process corresponding to it. So I mentioned the concept of a baseline, and that's really how we're able to flag a lot of these types of compromises. This doesn't just go for this particular case with Trivy, but really any of these supply chain incidents. Typically, what happens is, something executes in CI and it calls out to, the attacker controlled domain or a, command and control server. And those are typically domains that, obviously have not been seen before in those job runs. So that's how we can actually flag these or do active blocking on these. So in this particular case, you can see this domain that was reached out to is flagged as anomalous, and there's a little bit of an explanation is that is it was not included in the original baseline. Now, there's a little section here at the top. You can see kind of what was in the baseline. So these are some of the domains that have been seen over several job runs. But in this particular case, you can see that that domain, was brand new. It was never seen. It's not in the baseline. As a result, it's flagged as anomalous. You can also, just to get context, see a list of all the endpoints that have been called out to and how many times they've been reached out to. So you can see in this case, we lowered that threshold for the example, but the idea here is that it would flag this as a domain that has not been seen before based on that baseline. So this is an example of how you can kind of get notified on, domains that have been called out for the first time outside of that baseline. We can also show an example. We have block policies for this as well. So you can set not just an audit mode, but same idea. In this case, you can see that one-line script is actually resulting in this particular network being blocked because it's not explicitly allowed in the allowed endpoints list. So you can actually have a centralized policy for this, and that policy can get established from the baseline. So maybe over, 100, 1,000 job runs, however much you want to define, you can specify that, this is the baseline. Anything outside of that, it's going to actively get blocked. So that's on the hardened runner piece. I think we can quickly flip to kind of the second component here, which is more around how this attack executed. Varun and Ashish kind of drilled home the point around, this is more focused on this bot looking for, misconfigured workflows, and it would check if those misconfigured workflows can lead to, user input-based attacks. And I think we kind of went over, like the prompt injection and pawn request being kind of the primary means of some of these being exploited. So there's two views here that we can help with when it comes to, identifying where you're potentially impacted. So we have, these list of controls in our dashboard that kind of align to think of them as best practices, how you're potentially impacted, aligning to these best practices. Two of these here are focused on exactly these, which is kind of these workflow vulnerabilities. So pertain to, pawn requests and script injections. So these actually show you where you have potential workflow files that are misconfigured or potentially vulnerable across, your GitHub repository. So this kind of breaks it down in terms of what repository it's hosted in, what workflow is affected, and what's the risky trigger specifically for that particular case. So this is a really easy way to drill down. So if there is a particular example where you want to see, why this is vulnerable, it kind of breaks down exactly the step and line where that's potentially vulnerable. If there are multiple workflows even calling each other, it will show, multiple workflows here and kind of show you the chain on how that works. But the main idea here is to give you kind of a super high level view of where your potentially vulnerable workflows are to, essentially clean those up. The second piece is around GitHub checks. So this is something where it's more preventative, really more around preventing developers from, merging anything that is potentially vulnerable. So we have different controls here for our GitHub checks, and I'll show you what that looks like within GitHub in a second here. You can see we have some controls for NPM, and we have some controls for, the two that I mentioned earlier around pawn request and script injection. And the idea here is setting policies across your repositories where it would fail if there's PRs attempting to merge, anything that's potentially vulnerable. So what this would look like in an example of a PR, just to quickly go within a PR to show you, that check would run depending on how you defined it. So this you can see step security required checks ran here and it failed. And you can see there's several checks here that failed. So you can see, the pawn request and the script injection that failed. The idea here is to give you context on, in this particular PR, something's being merged or something's being changed or modified that's potentially in making this, workflow in a vulnerable state. So you can see exactly, what job it is, what line triggered it, and what the trigger specifically is. And you can get some context as to what exactly is happening. In this case, we're just merging an example of workflows that were potentially modified or potentially vulnerable based on some things like the PR target and, things like prompt injection where, potentially, untrusted, attacker code can be potentially executed. So that's an example of the GitHub checks and visibility on, the workflow files where you can see where you're potentially impacted. The last thing we can really quickly touch on is the developer MDM piece. So, I think it was Varun that was mentioning, they pushed a suspicious artifact to the Trivy VS Code extension on, VSX Marketplace. And as a result, you may want to, see where you're potentially impacted or where developers are potentially using that particular extension. So we have this, if I just went on this developer MDM section here, this kind of is around visibility and control on developer machines. So, what is exactly installed on developer machines from, an IDE perspective, package perspective. We also look at, AI coding agents and MCP servers. And just to give a little bit of context on how this works, it's basically based off an installation script. Once that script runs and it's deployed, you can push it with your MDM. It essentially gathers some data on, what devices have registered data, what plugins are installed, and all this other context here. So this is an example in this case, in this, demo platform, we have 9 different devices that are registered. You can go into each device and get some context on these devices. So this is an example where this particular device had that compromised version of that package, plugin installed. So you can see this actually flagged as compromised. The other view you can look at here is IDE extension. So this actually gives kind of a comprehensive overview of what IDE extensions you have installed. Right now it's for VS Code and Cursor across your developer's ecosystems. And we also have this security score, which kind of breaks down the risk of each particular plugin. And the idea here is that, if there is a plugin that's compromised, in this case, this Trivy extension, that'll be flagged here, and you can quickly kind of diagnose and triage that based on, whoever has that installed. You can quickly drill down into those devices there. And kind of on this topic, we do also flag things like, what AI coding agents are in use and MCP servers are in use. So this is definitely a trending topic where developers are using more and more coding agents. So getting visibility into that in one central place also lets you kind of control, what should and should not be used across your, developers' ecosystems. So that's kind of the 3 main components. Just to quickly summarize, so that hardened runner piece I talked about first is more around, the network monitoring. So really looking at any deviations from the baseline, if there's, new outbound networks that are being called out to, being able to A, audit them, or B, block them if you do decide to set a block policy. And then we talked kind of about visibility on the misconfigured workflow files so you can see where those exist across your GitHub ecosystem and also prevent them from being merged if they're being, potentially modified to, um, do something malicious or just be vulnerable. And then we talked about the MDM piece, which is really around visibility on the IDE extensions, coding agents, MCP servers, really anything in use across, your developer ecosystem. So I'll stop share there. I think Ashish, maybe we can go to a Q&A unless there's anything else you guys want to add on there.
Yeah, I think we can open up for Q&A. So we have one question from Jason. Will you guys be adding in capability to block things on dev machine, like if they have OpenClaw? So that capability, I would say, partially still exists. It already exists in our platform because right now, uh, the philosophy behind our developer MDM functionality is that we don't explicitly want to make any changes. So if you look at the way we are collecting the inventory, including AI agents such as OpenClaw, the system actually gives you the full path. So, and this is also true for npm packages. So if you use the npm search functionality to discover compromised packages on developer machine, it will give you the full path. And currently the scenario that our customers are following is they actually then take this data and then they feed it to their mdm solution, and they review it, ensure that it is true positive, and they indeed want to take a remediation action such as deleting the file or uninstalling like an AI coding agent. Then they feed it to their MDM solution, and then their MDM solution can delete um, a particular AI agent or file, and then you can rerun our script, which will confirm that it has indeed been deleted. Now, in addition to that, we also have a few features on our roadmap where we'll be using native like blocking features available in some of these platforms natively. So for example, soon we are planning to ship a feature for ID extensions where you'll be able to specify an allowed list. So the flow will be you use our platform to discover all the ID extensions that are in use, and then using this data you'll be able to create a block policy either for specific devices or for all the devices in your environment. And the way this allowed list will be enforced is by using uh, VS Code's native functionality, where you can allow, where you can specify an allowed list. And using that feature, you'll also be able to implement a cooldown policy for your ID extension. So once the cooldown policy is implemented, our system will ensure that your developers can only use a version after it's been around for, let's say, 2 days or 24 hours, and so on. So we do have, so currently our platform is collecting inventory, and using MDM, you can take some of these remediation actions, but we do have features on our roadmap where you'll be able to use our platform to also enforce, enforce restrictions and security policies.
Then we have a question around, has there been analysis on the downloaded script? And let me share my screen to answer this. And in this screenshot, you can see that there was this script that was being added by the hacker bot. And unfortunately, by the time we actually tried to get this script, this domain wasn't resolving. So we weren't able to download the script in time. But based on the actions that happened after this, we can make some uh, kind of guesses around what it was doing and what we are sure it was doing. So after this, we know that the Trivy bot was exfiltrated because after this, there was a uh, commit that was created using that bot. So we can be sure that this script, it was exfiltrating that particular token. And in other exploits, we have seen it had exfiltrated the GitHub token. So it was doing that. But to answer the question, unfortunately, we were not able to get the script in time. By the time we tried to get it, that domain had stopped resolving.
So I see that Sanchit has a question, and let me see if there's a way for me to, so that they can talk. I've not tried this option before, but Sanchit, could you please try to use your mic? See that you have raised your hand.
You can, feel free to post your questions in this webinar chat. And if you don't have more questions, if you wanted to just share any insights related to this incident, please feel free to share that as well. So the next question is, so even since we do not have a public repo, best practice would be to get away from using things like pull request target. So these attacks, they are much more relevant to public repositories, because if you have a public repository with pull request with the spawn request or script injection vulnerabilities, it's much easier to exploit, and anybody on the internet with a GitHub account can exploit it. So definitely the risk is much higher for these specific vulnerabilities for a public repo. At the same time, what happens is that you may have a private repository, and that that may become public in the future just because it was meant to be public and it started off as private. And there are not just this bot, but there are also other attackers that are constantly trying to find these vulnerable workflows. And so the time that you have a vulnerable workflow from that point to exploitation is now reducing. And so from that perspective, it's best to review and make sure you don't have these pawn request and script injection even in private repositories. But just from a risk perspective, the risk is much higher for a public repo.
Another point I would like to mention is that we have seen this several times where internal red teams actually use CI/CD as a way to elevate their privileges. So in a large organization, it's also a best practice to defend against insider threat, where you if you assume if you assume the principle of least privilege, you don't want, just to ensure that you have necessary security controls in place. It's actually a good practice to avoid pawn request vulnerabilities even in like private repos, especially for large organizations, where you have multiple users, or you may have you know um, external users, with access to your private repositories, external, like trusted users access to your private repositories.
So the next question is, does this attack impact other artifact repos like Docker images? Now, the way this particular, hacker bot claw was working is that it was starting off with the GitHub Actions workflows and it was trying to compromise those. But like we saw with Trivy, once the credential was compromised, there was a suspicious, in fact, there was a compromised malicious version of their VS Code extension, which was published to the Open VSX marketplace. So the same thing could happen with other artifact stores as well. So if there is a credential that is compromised, it may have started off from a GitHub Actions workflow, but that could then potentially be used to push malicious artifacts to other repositories, and that could be a Docker repository. Okay. Yeah, let us know if you have, additional questions. We still have 10 more minutes. Then, just to wrap up, we will be uploading this webinar recording to our YouTube channel. And if you have, any questions outside this webinar, you can always reach out to us through our website. I see there's another question, which is, when a token is compromised, can it be used from outside, like an external machine? So now this really depends upon what that token is. Each GitHub Actions workflow job has a GitHub token, and that token can only be used while that job is active. And so, in cases where you saw, like, I think there was one exploit where there was a file pushed through that using that token because that job was still active. But if that token is compromised, that is actually an ephemeral token. So if it is compromised and the job ends, then it cannot be used anymore. But if you have a persistent token, like a personal access token, like was being used in the Trivy repository, then it can be used from outside, and it can be continued to be used as long as it doesn't expire. And usually these personal access tokens, the expiration is really set outside the GitHub Actions workflow. So to answer your question, if it is a GitHub token, which is an ephemeral token, then it can only be used until that job is active. And for that, we have in the past seen attacks where the job just sleeps for a long time so that it doesn't finish, and till that point, the attacker can use that token to do reconnaissance and make changes. But if the workflow actually uses a personal access token or persistent token, then if that is compromised, it can be used even after the job ends. Okay, so there are no more questions. We can wrap up the webinar. Thank you again for joining and for these insightful questions.